Hello my dears, today we are going to focus on a new session, that is insulators. Insulators. So there are so many types of insulator in the power system, my dears. First of all, let's see pin type insulator. Actually, this is a very common type of insulator that we have seen in transmission line and all. I mean distribution, not transmission, it is a distribution line. Pin type instruments are used, it is used up to 33 kV, and normally we have seen it over 11 kV line, over 11 kV line, or up to 11 kV line, or up to 11 kV line, up to 11 kV line. Okay, and this will be the structure of the pin type insulator, my dears. So many pins are there, and there will be a groove for placing conductor. Groove for placing conductor, and this is the pin. Fixed to pole or pole arm, fixed to pole arm. Actually, it is, you have usually see this in distribution system that is near to our home and all. See, a pin type insulator you might have seen. So there will be the top portion, there will be a small groove, it is called a groove or a small imprint. On that there will be conductor. So here will be the position of the conductor, and this lower portion, it is normally a pin. That pin is connected to the cross arm, that means fixed pole arm. This is the pole and this is the arm, right? This is the arm, right? So normally that pin will be here, that pin will be here. So that is the structure of the end, over which we can see the transmission line, So that's all about the pin type insulator. Next one is suspension type insulator. These are used up to voltages greater than 11 kV. These are used up to voltages are greater than 11 kV, or normally this will be the structure. You might have seen this, right? Here will be the conductor. Okay, so this is nothing but metallic link. And see, did you see this in the big towers now? when we are traveling along the road or rail, you might have seen very big towers that may carry very high powers, my dear, very high voltages, not power, very high voltage as well as power, very high power or voltages greater than 66 kV or 132 kV, etc. So that type of transmission, it is actually seen in the transmission system, not in the distribution line. So in that type of transmission, you can see that there will be a what? Suspension type insulator. And the peculiarity of this is the suspension type insulator is that it consists of so many discs, my dear, so many discs. This disc can carry up to, each disc, I can say that each disc can carry 11 kV of voltage. Each disc can carry what? 11 kV of voltage it can carry. So suppose if any one disc is what damaged, what is the main advantage of using this suspension type insulator is that if any one disc or this disc or disc is damaged, you can simply replace it and insert another new disc so that the whole system will work again. But in the case of this pin type insulator, and if in between this disc is damaged, means we can't replace it. We have to replace the whole system. We have to replace the whole system. Okay, so that is the peculiarity and the beauty of this suspension type insulator, is that we can replace every or each disc we can replace. So each disc can carry 11 kV. For example, suppose a 132 kV system. This 132 kV means it is a line voltage. It is a line voltage. So we assume that the transmission is star connected. So what we have to do, first we have to convert it into phase voltage. So it will be 132 divided by √3. You will get nearly, my dear, 76 kV. It is nearly 76 kV. Okay, which means each disc can carry 11 kilowatt, means for 76 kV maximum 8 disc you can use. 8 disc you can use. So such a line, 130 kV line, there will be 8 disc suspension type insulator. So that is how we have to calculate for the how many discs are there in the suspension type insulator. For example, a 66 kV line, my dear, 66 kV line. So 66 kV means 66 divided by √3, which is nearly again equal to 38 kV. So 38 kV means 11 into 4, 44. Na? So maximum 4 to 5 disc can be used. Disc can be used. So like that, a question may be asked, see, for 66 kV line, how many discs are used? For 132 kV line, how many discs can be used? Means simply divide by √3, because line voltage equal to √3 into phase voltage. This each disc, my dear, can withstand the phase voltage, not the line voltage. Okay, can withstand the phase voltage, because a phase is connected here, not in between line it is connected, a phase is connected here, so this can withstand the phase voltage. So every voltage should be converted into phase voltage before calculating the strength of the insulator. Okay, so 132 line voltage equal to √3 into phase voltage, so that phase voltage will be line voltage by √3, so 132 divided by √3. And one more thing for problem solving, my dear, I will tell you a trick, that is, in every question, suppose it is regarding the three-phase system, the given quantity that is always in line quantity. That is always in line quantity. So whenever there is a demand of phase quantity, you have to convert it into corresponding phase quantity and do the calculation. Okay. So that's all about the what? Suspension type of insulator. Okay, my dear. Power system is normally the theory. Problems are also there, but more than that theory will be there. More than that theory will be there. Next one, string efficiency. Very, very important session. See my dear, this is the structure of a 3-disc, three disc string insulator. So this is nothing but my dear cross arm. This is the cross arm. That cross arm is directly connected to the earth, and the equivalent circuit of this will be equal to see my dear, there is two type of conductors. There are two types of capacitance will be formed for this type of string insulator. A string means nothing but this, each disc is also called a string, or each string suspension type insulator, there may be two type of capacitors formed. One is called the series capacitor or mutual capacitance, and second type of capacitance is called shunt capacitors or ground capacitance. Shunt capacitance or ground capacitance or stray capacitance. And let's check where are they formed. Where are these two capacitors formed? So for that I am going to take its equivalent circuit. So this is also grounded. This is the cross arm, and there is our insulator. See my dears, this is the metal conductor. Am I right? This is a metal conductor and this is a metal pin. Okay, and see here, this is a metal pin. So this metal pin is ultimately, this is an insulator. Okay, I am fine. And this is again a metal pin, and this is and finally it is connected to a conductor. So there is always a small leakage current through this, right? A small leakage current through this. So in short, what I am going to say, each disc now my dears, this disc, okay, consider this disc. So this disc, one end is connected to the ground and the other end is connected to another conductor. This disc, now consider this disc, one end is connected to the ground and the other end is connected to the another conductor. This is a metallic link now, so it is a conductor. This is a metallic link, correct? Metallic link. So it attacks a conductor. So this disc is nothing but a porcelain carrier or anything. Okay, any good insulating material is act as a disc. So an insulating medium in between two conducting medium, that situation arises there. So what happened my dear, so there forms a capacitance, one disc. So other disc also the same thing. This is an insulator, one conducting and another conducting metallic link. So there will be a conductor, in between an insulator. So there is also a capacitor. Similarly, there is also a capacitor. So how many number of discs are there? That much capacitors are formed. This capacitor now my dear, this capacitor is represented by C, and this is called the series capacitor. This is called the series capacitors. Okay, and here we are connecting the conductor. And one more thing I have to note is that this cross arm is also a conductor now. This is connected to the earth now. So earth also contains so many charge carriers. So this is also a conductor. And see, this is also a conductor, my dear. Not this, because it is actually connected to this. So you can't consider this. This is a conductor and this is a conductor. So in between that there will be a capacitance. So after the first disc my dear, there may be a capacitance. Is it correct? And after here also, see, after the second disc also there may be a capacitor. This is a conductor, this is a conductor. In between air is the insulating medium. So there may be also a capacitor. Check here, it is a conductor, and it is also a conductor. But see my dear, there is what? A high tension, our conductor is moving there. So we can't consider for this, okay, because it is directly connected to a conductor now. So the possibilities of making These capacitors are just here and here, that's all. Because this is a metallic link, this is a metallic link, not the conductor. This is a metallic link, and this is also a small what earth cross arm. These also contain small charge carriers, these also contain small charge carriers, so there will be capacitance. These also contain small charge here, these also contain small charge carriers, so there will be capacitance. But this contains huge charge carriers, because it is a transmission line. The bottom of this string is connected to the transmission line, so we can't go for array here and here will make a capacitance. No, it won't. There it won't we won't make any capacitance here. There. Is it clear, my dear? Is it clear? Okay. So the number of capacitance, shunt capacitance, should be always 1 less than that of the series capacitance. So these capacitance now, my dear, these capacitance is called the shunt capacitance, because it is shunt. It is shunting the transmission, the string with the ground. That is why it is called the shunt capacitor. And there may be the ratio of shunt capacitance to the series capacitance. Okay, which means the shunt capacitance is C shunt divided by series capacitance is C. So C shunt will be equal to K times C. C shunt will be equal to what, my dear? K times C. So this capacitor can be represented by KC, KC. This capacitor can be represented by KC and KC. So there the concept of two types of capacitors in the string or the suspension type of insulator. And one more thing you have to note that, my dear, we are now going to derive the expression for string efficiency. Now we are going to derive the expression for string efficiency. Okay. Cross arm, metallic link, cross arm, this is porcelain. Okay. So now we are going to derive the expression for string efficiency. It's very, very important. String efficiency is nothing but, my dear, see, suppose this is the conductor now, so there is always a current, right? There is always a current which is flowing here. Let I3 be the current here and small I3 be the current here, and after this let I2 be the current, capital I2 be this current here, and small I2 be the current here. Okay, small I2 be the current here. Let this capacitor, first capacitor now, it can carry up to a voltage of V1, let it be V1. The second capacitor now, it can carry a voltage up to V2. The third capacitor now, it can carry a voltage up to V3. Okay, there are three discs actually. So the first disc can carry up to a voltage V1, second disc can carry up to a voltage V2, and third disc can carry up to a voltage of V3. After that the disc will break and this the string will burst out. Okay, the string will burst or the string will destroy. So that voltage is called V1, V2, V3, etc. And we have to derive the, there is a derivation actually, to a big derivation is there, but we don't want the derivation, but the expression for string efficiency only we want. The string efficiency is nothing but, my dear, total voltage across the string, total voltage across the string divided by number of disc into number of disc into the voltage of string near to conductor, or I can say that total voltage across the string means, I already told you, this capacitor can withstand a voltage V1, this capacitor can withstand a voltage V2, this can withstand a voltage V3. So I can say that V1 plus V2 plus V3. That is the total voltage across the total string, my dear. This is the total string insulator, I mean suspension insulator. So V1 plus V2 plus V3 be the total voltage it can withstand. The three disc the total voltage that those three discs can withstand is nothing but V1 plus V2 plus V3. V1 plus V2 plus V3. Okay, so divided by number of discs, let be N, into voltage of string near to conductor. The near to conductor, this is the conductor, my dear. What is the voltage withstanding power of the string or disc near to the conductor? It is nothing but V3. So into 100. So that is called percentage string efficiency. Very important relation. Very important relation. So V1 plus V2 plus V3 whole divided by N into V3 will be the equation for what, my dear? String efficiency. So how this can be obtained and all, and how we can apply this concept and all, we will do a problem and it will be clear. And suppose you have a value of V3. Suppose you have normally in question there definitely the value of V3 will be given, or sometimes the V3 will not be given. So at that time the line voltage, now my dear, the line voltage definitely given. So we will connect this V1, V2, V3 with the V, that is the apply. This is the total voltage, total line voltage. We are going to derive the equation actually, but the derivation is also we don't want. Only the end results we want, and just by heart this equation and it is enough. Okay, my dear. Okay, so V1 will be equal to V divided by 3 plus 4K plus K square. Equation number 1. And if you have V1, V2 equal to V1 into 1 plus K, and V3 equal to V1 into 1 plus 3K plus K square. These are the very important relations you have to mug up. It is very helpful for solving problems, my dear. It's very helpful for solving the problems. Okay, so from this equation you note one thing, or from here you can observe one thing. See, this is the conductor, my dear. This is the conductor. So this string is having the maximum stress here because it is directly connected with the conductor. So the value of the voltage withstanding capacity of the third disc, my dear, of the third disc V3 should be very high. Should be very high. That means these discs can withstand high voltage compared to all other, because this is directly connected to the line. And see the next disc V2, I mean this V2 disc, this voltage will be less than that of this voltage, of course, because this is not directly connected to the conductor. It is after effect, I mean the current after flowing here, then it will be flowing there. So this V2 now, my dear, this is less than V3, and finally this V1 also. This is a very important relation in what suspension type insulator. So maximum voltage capacity of the string will be the string near to the conductor. This will be have the maximum voltage carrying capacity, or maximum stress handling power is nothing but this conductor should have, I mean this insulator should have this insulator, my dear, this capacitor or insulator have the maximum stress carrying capacity, and in this equation, and K is nothing but, my dear, ratio of shunt capacitance by series capacitance. That's all. So only this 1, this 2, 3, 4 and the relation, only this is enough for solving any problem in regarding the string efficiency. Okay, we will do a problem so that it will be very clear to you. It will be very clear to you. Okay, my dear. Okay, my dear. And the value of the K will be always less than 1. K will be always less than 1. That also you should note. Okay. Okay, my dears. And I already told you the voltage distribution across the strings is not uniform. The maximum stress is faced by the disc near the conductor, and the minimum stress will be faced by the disc away from the conductor, or disc directly connected to the cross arm will face minimum stress. Okay, that also you should note. Okay, let's do a question so that these things will be very much clear. Okay. Next, in a string of 3 disc unit, question. If earth capacitance is 10% of cell capacitance, full stop, then find, full stop, then find the voltage distribution across the string across the string, comma, and string efficiency. And string efficiency if the maximum permissible voltage across any string is 20 kV. This is the question, my dear. This is the question. Read the question carefully. So this type of question you may expect for your examination. So in a string of 3 disc unit, right? 1, 2, 3. Here will be the conductor. Okay. If earth capacitance is 10% of self capacitance, that means earth capacitance equal to 10% of self capacitance, or earth capacitance by self capacitance 10%, it is nothing but 0.1. Earth capacitance is nothing but, my dear, Kc, am I right? Kc divided by self capacitance is nothing but C, equal to 0.1, implies K is equal to 0.1. That is why this data is given for finding the K. So K you got 0.1. Then find the voltage distribution across the string means this can carry up to a voltage V1, this can carry up to a voltage V2, and this can carry up to a V3. So find the V1, so we have to find V1, V2 and V3. These things you have to find. The string and string efficiency also you have to find. String efficiency also you have to find. Okay, if the maximum permissible voltage across any string is 20 kV means That means, my dear, this disc can carry up to a voltage of 20 kV. This disc can carry up to a voltage of 20 kV. This disc can carry up to a voltage of 20 kV. Any string can carry maximum voltage of 20 kV. But what is actually 20 kV loaded? Where actually 20 kV loaded? This can carry 20 kV, okay, I agree. This can carry 20 kV, I agree. This can also carry 20 kV. But in practice, suppose it is connected to a line, which string is actually can carry, or which string is actually carrying 20 kV? Which string is actually stressed with 20 kV? This disc now, because it is directly connected to the supply. So that means, from that concept, my dear, you have to say V3 is equal to 20 kV, because not V2 is equal to 20. V2 is means maximum V2 can be 20 kV, maximum V1 can be 20 kV. But in put into practice, actually the load full bearing is who? The V3 or the least disc, or that disc voltage is given as 20 kV. So now you have V3 in your hand, my dear, V3 in your hand. So we have the relation V3 equal to V1 into what? 1 plus 3k plus k square. Am I right, my dear? 1 plus 3k plus k square. That is V1 into 1 plus 0.3. 0.3 into 3 into 0.1 is 0.3 and 0.1 square. If you substitute this, and this is 20 kV, na? 20 kV. If you substitute this, and you will find the value of V1 as 15.26 kV. So what is the inference here? This V1 is actually, it can carry up to 20 kV, okay, I agree. But in actual practice, the voltage across this string is not 20 kV. Maximum it can carry 20 kV, my dears. But now it is not carrying 20 kV, it is just carrying 15.26 only. Fine. So if you have V1, you can calculate V2 also. V2 is equal to V1 into 1 plus K. So it's nothing but, my dear, V1 is nothing 15.26 kV into 1 plus 0.1. So you will get V2 as, V2 is nothing but, my dear, 16.79. What is that? 16.79 kV. So now you have V2 also in your hand, V1 also, V3 also, everything is there, and this is the voltage distribution. V1, V2, V3 are the voltage distribution across the string. And what is the string efficiency, my dear? String efficiency, or efficiency of string. String efficiency is nothing but what? V1 plus V2 plus V3 all divided by N into V3, which is nothing but, my dear, add V1 plus V2 plus V3, V1 plus V2 plus V3, simply add both 3 into V3, which is nothing but, my dear, if you substitute this, you will get 86.67 into 100 also there, my dear, into 100, okay, into 100 also, percentage na, so percentage na, you have 86.67 percentage. So that is the final value of string efficiency. That is the final value of string efficiency. Okay. So when the string efficiency will be 100%, each disk is equally distributing the voltage. In practical, put into practice, when put into practice, each disk is equally distributing the voltage. That will not happen. Surely that will not happen, because that's an ideal case. So at that time, V1 will be, V2 will be, V3 will be equal, so that V1 plus V2 plus V3 will be 3V divided by 3 into V. 3V and 3 will cancel, 3 and 3 get cancelled. 100% efficiency you can get there. 100% efficiency you can get there. So is it clear, my dear? So this is how you have to solve a problem regarding the string efficiency. Okay. Is it clear? Is everything is clear to you, my dears? So everything is clear to you? Next, Methods to improve string efficiency. Methods to improve string efficiency. First method, by making k equal to 0. Why I said so? Because the reason for the unequal voltage distribution across the string is the actual reason for the less efficiency, right? V1, V2, V3 all are different now. Suppose all are equal, V1 equal to V2 equal to V3, then what happened, my dear? String efficiency will be 100% and super adipole string, right? And nice insulator will be there, string insulator will be that. So that is not possible every time, because it is only an ideal case. So what is the reason which hindering the ideal case, my dear? The reason which hindering the ideal case is nothing but the shunt capacitance, or K. The shunt capacitance, my dear, the shunt capacitance. If there is no shunt capacitance, then what happen means there will not be any current. See, this is nothing but the series capacitance, my dear, and this is nothing but the shunt capacitance. Okay, the presence of this shunt capacitance to the series capacitance actually make the ratio K, and that K that is the reason for different voltage distribution. If there is no K, means there will not be any shunt capacitance. There will not be any shunt capacitance. The capacitance will be only this one. The capacitor will be only this one, these three capacitors. If three are the capacitance, means the current here will be same as that of the current here, because there is no this capacitor, and the current will be same here. So that same current will be flowing through each of the capacitors, so that voltage distribution of the whole capacitor, that each capacitor will be I into XC will be same. Voltage drop this drop is nothing but I into XC. This drop is nothing but I into XC. This drop is nothing but I into XC. If you make capacitors equal, then the voltage distribution also same. Then the voltage distribution also same. But that is not possible because of the presence of this KC. These all C, but there will be KC also. That KC is the real problem makers. That KC is the real problem is, or the shunt capacitors are the real problem, because a part of the current will be flowing here, so that the remaining current will be only flowing here. Again a part of flowing here, only the remaining will flow here. That is the reason why the unequal currents are the reason why the presence of K, the unequal distribution of current is the reason by unequal voltage drop across each string. This unequal current this is, suppose this is 10 ampere, you injected a current 10 ampere here. Okay, 10 ampere come here, suppose 1 ampere goes here, only 9 ampere will be here, and 9 ampere can be 1 ampere again goes here, only 8 ampere will here. So 8 ampere into XC will be the voltage here, 9 ampere into XC will be the voltage here, 10 ampere into XC will be the voltage here. So which voltage will be higher? This one will be higher, this one will be lesser, this one will be least. Okay, why this unequal distribution happened? Because of the presence of this shunt capacitor. So how can we eliminate that shunt capacitor, my dears? The capacitance equation C is equal to epsilon A by D. So for reducing the capacitor, only thing you have to do is increasing the distance. Now the distance means this distance, this distance you have to increase. Array, how much you can increase? This is a cross arm and this is a insulator. Your insulator is in, you imagine it is in Kottayam. You can't place this insulator at Thrissur, right? You can't place this. It is practically impossible. By maximum distance you can get. Or this is in Trivandrum and this is in Kasargod, both end. You can't place like this for making maximum distance. So this method by making zero, this is not practically possible. This is not practically possible. So that is the first way of but improving the stream efficiency, but is not practically possible. And what is the next method? What is the next method? Next method. Capacitance grading. That means what we have to do, my dear, the least capacitor the least disc can carry a current of, suppose it be I3, let be I3 I3 into XC3. The voltage drop across the least capacitor, the third capacitor will be I3 into XC3. You imagine that should be equal to I2 into XC2 that should be equal to I1 into XC1. If this is happen, then equal voltage drops will be there. Okay. If this is happen, I3 into XC3 when equal to I2 into XC2 when equal to I1 into XC1. If these equations satisfy, then I can say that each capacitor can withstand the same voltages. I mean, it can carry same voltages, so the string efficiency will be 100%. So I3 is, you know one thing, man, I3 greater than I2 greater than I1. You know this, correct? You know this, correct? If I3 is greater than I2 is greater than I1 means, according to this relation, I can say that XC3 less than XC1 less than XC2. Am I right? Because I3 into X3 equal to I2 into X2. It will be a constant. So if I3 is higher means XC3 will be very least. Then only it will be a constant. So XC3 less than XC1 is XC2. XC is nothing but, my dear, 1 by omega C3 less than 1 by omega C2 less than 1 by omega C2. C1. Or I can say that C3 greater than C1 greater than C2. Is it correct now? C3 means we have epsilon A by D, correct now? Epsilon A by D. So I can say that A3 greater than A2 greater than A1. So for making the voltage distribution same, my dear, equal, what is the only thing you have to do? The capacitance near to the conductor having maximum area and least area should be the capacitor or the string near to the cross arm. So by this arrangement or by this gradation of the capacitor is called the capacitor grading. Is called the capacitance grading. But this is also practically not that much super, right? Because you have to make some bigger area and smaller area and that is also, there is some drawbacks also, there are some drawbacks also, because sometimes the fault, sometimes in the transmission line there may be a high current flowing situation happens. Okay, so what happens means these things will be suddenly in unbalanced condition, and this will not be satisfied there. So there may be some chances also there, and lightning, when the lightning comes and all, there may be another problems arise. So this is also not practically possible. So this is also not practically used. Alright, sir, then what are you trying to say? Is there any practical method? Yes, that is called, third one is called the gartering method. This is, you might have seen in the transmission line that I will tell you. A simple conductor will be a projecting like this. You might have seen a conductor will be projecting like this. You might have seen, definitely you will see that. This is called the gartering. And what is the function of this gartering, my dear? I will tell you once that this is KC and this is KC. It is carrying a current small I3, and this current is nothing but, my dear, capital I3. This is I2 and this is carrying a small current I2. So what happened means, this is a conductor now, this is directly connected to a conductor, so that these all contain high currents. This all contain what, my dear? High current. So that there is a chance of making a capacitance here also. there are chances of making capacitance here also in between this metallic link, because this is metal and this is metal. In between that there is a what? There is a capacitance. So this capacitance now, my dear, this can carry a current I2 and this can carry current I3. This can carry a current I3. Okay. So what happened actually here? What's happening actually here means the current requirement of this capacitor now, this is fed by this capacitor, because this current is coming here and this is met by here. This current is come here, and for this current now there is a requirement of I3 here. That I3 will be provided by this. There is a requirement of I2 here. That I2 will be provided by this, so that this I3 will be equal to this I2. This capital I3 and capital I2 will be same. If capital I3 equal to capital I2 means, definitely you can say that I3 into XC3 will be equal to I2 into XC2 if you are using same value of capacitance. So this condition arises there, so that voltage distribution across each disc will be same. Voltage distribution across each disc will be same. Okay? Okay, my dears? Is it clear? Okay, so that string efficiency will be improved. String efficiency will be improved. If voltage distribution is same, means string efficiency will be improved. String efficiency will be improved. Okay, of course, which is equal to, you can add one more thing, I1 into XC1. I1 into XC1. Okay. Because this I2 is smaller, remaining current will flow here. There is nothing to flow here, so same current will be flow here. Simple. So you can say like this. So string efficiency is finally improved. String efficiency is finally what, my dear? Improved. Okay. So this is the method actually we are using in transmission line. Like a strain insulator. It is same as that of, same as suspension, but used in dead ends and mounted vertically, not horizontal, mounted horizontally and mounted horizontal. That means you might have seen like this, my dear. The same insulator, suspension type insulator, that is mounted what? Horizontally, not vertically. This is happening when there is a dead end. Dead end in the sense means there will not be any transmission after that. So that means suppose this is one pole, this is one pole. There will not be any transmission line here, means we can't hang like this. Only we can hang like this. Hai? You can't hang like this because there is nothing here to support it, the hanging. You can only hang horizontally. That is why simple. So dead end will be that type of insulator is called strain insulator. Why the name strain means? This time the insulator is not carrying only electrical strain but also carry the mechanical strain, because that is in near end now. I mean farthest end, right? So it can carry the strain also. That is why the name strain insulator. Another type of insulator is nothing but a shackle insulator. This is normally seen in the 230 volt system or 440 or 414 volt system. Now this type of system you can usually see this shackle type insulator. This is nothing but, my dear, a pin type of pin insulator itself. But there will be a shackle like this. There will be a shackle like this, and you can carry the shackle, my dear. Actually, there will be a shackle. You can carry that. You can carry that. The groove will not be in between here or in midway also. In midway also there will be grooves to carry the conductor, and you can shackle it here. You can shackle and you can screw it here and here. You can screw here and screw here. It will be steady. Okay, shackle type insulator. So it is normally seen in low voltage transmission line, low voltage distribution. You can see here low voltage distribution, low voltage and low tension. Low voltage and low tension distribution system. Okay. Next, corona losses. Not the corona now we are facing, but another type of corona is faced by the transmission line, especially the high voltage transmission line. See, my dears, suppose this is conductor A and this is conductor B. Okay, this is high voltage carrying conductor and this is also high voltage carrying conductor. If there exists a voltage in between these two, or there is a potential difference, or there is a stress of 21.2 kV in between these two conductors per centimeter, my dear, per centimeter. Suppose these are separated by 1 centimeter. So at that 1 centimeter length, there will be a, suppose you imagine there will be 21.2 kV centimeter RMS or 30 kV per centimeter peak or maximum. If this much voltage is existing per 1 centimeter length, my dear, what happened? The air in between these two conductors, this start conducting, this start ionizing, and there will be a short circuit happening. If this is in 1 centimeter, means there will be a complete short circuit happening, and the air between these two conductors start conducting. So did you notice one more thing? Actually the air is a perfect insulator or very good insulator. Not perfect, very good insulator for electricity. But what happens when lightning arrives? When lightning arrives, my dear, so this is the earth and this is the what? Megam, right? Megam, or what is the English word of megam? What is the English word of cloud? Yes, cloud. Suppose this is the cloud. Okay, so suppose the voltage here or in between 1 centimeter, that means up to a 1 centimeter, if there is existing voltage of 20.2 kilovolt RMS for 1 centimeter, then that air will start to break down and that air will conduct. If it continuously happening, then there will be the lightning. So that is why we are seeing like this lightning. This is actually the conduction of air. So air also can conduct if a maximum stress of 21.2 kilovolt per centimeter exists in the air. That is called the breakdown strength of the air. That is called the breakdown strength of the air. Okay, before I am going to the corona, this should be very important thing. Okay, important thing you have to know. So in high voltage transmission, my dear, in high voltage transmission, suppose there are two conductors like this, two conductors are like this. If there is a particular voltage existed in between these two conductors, that what happened means there will be a faint violet glow with hissing noise with the production of ozone gas called corona. So what is corona means? What is corona means? For a high voltage transmission line, if certain conditions are satisfied, that condition I will tell you. If certain conditions are satisfied, then around the conductor, my dear, you can see a violet glow. You can see a violet glow around each conductor. That means each conductor is glowing now. Start glowing, and there will be a hissing noise also, with the production of ozone gas, or ionized ozone gas. That is called the corona. Okay, I will tell you another important thing now. Okay, corona is there. Okay, corona. Critical disruptive voltage. VD. This is the minimum voltage at which corona starts. It's a minimum voltage at which corona start is called the critical disruptive voltage, or visual critical disruptive voltage also say sometime. That is called visually we can see the corona. There may be corona, but visually you can see that faint glow and all. Now, that is called a visual critical voltage. It's not that much important. That is greater than this critical disruptive voltage. Okay. Because even though the air is ionized and small gases are producing, but for a human being it should be notable now. That should be up to a certain level now. That is why it is called a critical disruptive voltage. Is the voltage, minimum voltage at which the corona start. This corona start means at the starting itself. It is not necessary that we can't see our naked eye, with our naked eyes. It is not necessary that you can directly hear the noise with very loud manner. No. It is the voltage at which the corona started. But there is another voltage, my dear, critical visual disruptive voltage. That voltage is the voltage at which we can feel the corona, we can see the corona, we can hear the corona. Okay, that is the called critical visual disruptive voltage. Okay, leave that. Focus on this. So critical disruptive voltage, this is the minimum voltage at which corona start, my dear. So VD will be equal to this is the expression for what critical disruptive voltage VD. M is nothing but, my dear, surface irregularity factor, and G is nothing but 21.21 kilowatt per centimeter RMS, or 30 kV centimeter maximum. It's a constant. And radius of conductor. Del is called air density factor. It is nothing but, my dear, (3.92 B divided by 273 plus T, where B is nothing but barometric pressure. And T is nothing but absolute temperature. Simply temperature in Kelvin. Temperature, Kelvin of degree. Degree. So barometric pressure and temperature in degree. So degree, correct. mgr del is equal to, that's all. So this is the expression for mgr del into ln d by r. D is the distance between line. So if this much voltage is existing between two phases, this much kilovolt is existing between two phases. Between two phases, my dear, what happened? There will be corona. There will be corona. I already told you 21.2 kilovolt is exists for 1 centimeter, there the air will be breakdown. But this is not 1 centimeter now. Two lines are moving like this. This is not 1 centimeter, it is some meters away. So what will be the voltage? So this voltage will be critical disruptive voltage. That voltage is a critical disruptive voltage. Okay. So this is the minimum voltage at which corona starts. Minimum voltage at which corona starts. Okay. Now expression for corona loss or power loss due to corona. P is equal to yes. This is the expression for power loss due to corona. No one will ask you this equation, but the things, power loss is directly proportional to frequency. Power loss is inversely proportional to root of D. Power loss is directly proportional to R. Power loss is directly proportional to inversely proportional to del. These things you have to know. Okay, the problem regarding this will not be asked, but the relationship with respect to every term now, that will be definitely asked. That you have to note. And from this expression it is clear that for DC F is equal to 0. So P due to corona is lesser compared to AC. Compared to AC. Also, and for bundled conductor, what is for bundled conductor, my dear? GMR will be high. That is the geometrical mean radius will be high for bundled conductor. So that, see the expression for VD. See the rooted thing you just forget. See the expression for VD now. In VD, MGR means radius of the conductor. If it's a three-phase line, means GMR, geometrical mean radius, bundled conductor. So if R is higher means GMR will be higher, VD will be higher. So only at higher voltages, corona will take place. Corona will take place. So that if you use a bundled conductor, the chances of the corona will be lesser compared to non-bundled conductor. That's all. Non-bundled conductor. Is it clear, my dear? Is it clear? Is it clear? Next one, advantages of corona. Advantages of corona. Actually, there are two advantages, my dear. One advantage is that effective radius conductor increases. Why? Because see, this is the conductor initially. If there is a corona means a globe will be there around now. So the effective radius will be what? This is the radius first. So now this will be the radius. So the effective radius will be increased means R is equal to rho L by A. If the Radius is increasing means the area of cross section also increases, so that R will become lesser if this will become high. Am I right? So the resistance will be decreased. So the prior to corona, the corona affected line having very least resistance, so the current power can be easily flow. And the second advantage is that ionized air, the ionized air around the conductor makes an envelope, and lightning will hit on that envelope and absorbed by that envelope, by that. So lightning doesn't affect the line. That means there will be a gas or ionized or conducting media envelope around the conductor, so the lightning will be struck on this only, not the conductor. So the conductor is safe. So these are the advantages. And of course one disadvantage will be there. That major disadvantage is that, my dear, what? The major disadvantage is nothing but the power loss. I've already explained, the mentioned the expression that power loss will be always there. Power loss is nothing but the loss, the efficiency will be decreased, right? So that is the major disadvantage. So that's all about today's session. Let's meet again tomorrow with a new session. So until then, bye, take care.